warahmatullahi wabarakatuh. In this lecture, we will start the sensors, which is the first topic of the industrial automation that we're going to cover, inshallah. So we will be discussing what are the different types of sensors available in industrial setup, and then slowly we will go to signal conditioning and signal processing and all these things. So in the sensor aspects, we will be covering sensors, signal conditioning, signal processing. So let's talk about the sensors first. So basically, there are various ways to classify the sensor. A common ways to classify as follows: contact sensors and non-contact sensors. So the contact sensor is basically the sensor needs to touch the object to sense it. For example, it's a mechanical limit switch is an example of contact sensor. Whereas non-contact sensor is it doesn't need to physically touch the object to sense. Optical limit switch is an example of non-contact sensor. Um, these types of sensors are usually fast in response but less reliable compared to the mechanical contact sensor. Whereas in the mechanical limit switches or micro switches, usually because it's a mechanical nature, so for it cannot respond with high frequency input. It will be usually slower in responding for high frequency input. You can also classify the sensors in digital sensor or analog sensor. Digital sensors means the sensor can give either present or absent of the object, 1 or 0. So usually limit switch counters, these are the types of sensors used as a digital sensor. Whereas when you have a continuous variable, we use analog sensor, which is like pressure sensor, current sensor, flow sensors, force sensors, strain gauges. These are considered as analog sensors. Uh, so these are the another two type of categories that can be used for sensors. Now this is an example of a uh, digital sensors for on-off the light bulb. So if it senses the object in the transistor, it will turn on uh, this transistor switch will be shorted and the load can be carrying the current. Light sensing is on when the light is present. Dark sensing is on when the ambient light is absent. So these are example of digital sensor is optical type. Um, for it is already used in street light, automatic controlling of the street light or building corridor light. It can be used for. Okay. Usually digital sensors, like optical digital sensor, one common type is reflective sensor. You have let me draw it here, then you will understand better. Let me put my writing pad attached to this computer. Okay. Okay. So usually this would look like something like this. You have a sensor package like this. You have an emitter and a receiver. So the light, and you have an object to detect here. So the light goes here and gets reflected, and this is how you detect the object. So emitter sends out the light and the receiver senses the reflected beam from the target, and usually the sensing distance is within 1 millimeter, very low. It is within 1 millimeter. You cannot sense the object with long distance. Then to increase the distance, what you do, you have a retroreflector far away from here, and then you have an emitter here. This is the emitter, and this is the receiver here. So it gets reflected from the retroreflector, and if there is an object in between to break this path, so then you will have the object to be sensed because this optical path is broken. However, it has a problem because if this object is shiny, so it will also reflect the light beam. So the path will be broken, but the sensor will sense the path is not broken because it can still receive the light. So this is the problem of retroreflector, as sensor distance is higher, but uh, it will have this problem. To overcome this problem, what they do is using polarizing photosensor. So this is the polarizing photosensor where light is unpolarized. Usually light you would say is an unpolarized light. So unpolarized light, if you do a cross section of the light, it goes all the way, like this way. It is vibrating in every direction. So this is the electromagnetic vibration in any direction. So if you send this light through an polarizing filter, so you send this light source, you send this light with a polarizing filter, horizontally polarized, then this special type of retroreflector will change the polarization of the light to vertically polarized light. And because this vertically polarized light, and then the filter is vertically polarized, so it will be able to sense the light beam. So now let's say you have a reflective object connecting, bringing in here. It doesn't have the capability of changing the polarization from horizontal to vertical. So it will still send back the horizontally polarized light. And as the filter is vertically polarized light filter, so the filter will block this light, and this will not be able to detect the light. So this is how you can still detect a reflective object with this mechanism. Now, also you can have emitter. This is the emitter, and this is the receiver. Usually in lifters, in passenger lift, you will have this type of sensors. So if the object blocks this light, so basically it will detect the object, and the way the passenger lift door is operated, if you put your hand in between the door when the door is closing, it detects the object and the door becomes open again. Now, sometimes you have convergent photosensor. Basically, you have similar emitter, and basically you have a receiver, same package, but on top you have a uh, lens. So basically you try to converge this thing to this way, so you have a convergence. So this is type of convergent photosensor, not so popular, but laser sensor is very, very popular as on because it can do a long distance measurement, and it can, because the laser spot can be as low as 5 micrometers, so you can detect a very tiny object in dimension. Okay, now the most important thing in industrial automation in any servo mechanism is uh, encoder. It is a kind of sensor to count the revolution of the revolutionary speed, and as well as the rotational distance, rotational angle of the motor that you would like to know. So basically you have a light source, and it passes through a series of series of windows, and you can have a light source here, and you have a light detector here. So the window is something like this. These windows something like this type. So you have if you see the window, it will have opaque, transparent, transparent, opaque, something like this. So you have, there's a opaque, so you have dark here, and this is a transparent window. Then you have again dark, and then you have transparent, then you have again dark. So here how this is the arrangement of these things. You have dark, pop, transparent, dark, transparent, so on and so forth. Excuse me. So now let's say if you shoot the light from here and the detector detects the light. Now if you start to rotate this wheel clockwise or counterclockwise, so sometimes you will receive the light, sometimes you will not receive the light. So if you connect this sensor to an electronic circuit, so once the light is received, it is signal gets high. When the light is not received, signal gets low. So you will have a series of pulses received by this sensor as it is attached to the microcontroller. Now, if you start to count this number of pulses through your microcontroller by triggering a counter, then you know each count, how many counts has been rotated. You can calibrate this rotation with this number of count. So usually this whole rotation will give you 2000 pulse. So in one whole revolution, you will have 2000 pulses. So that's why. So if you receive a signal of, let's say, 200 pulses, meaning to say your uh, shaft has rotated 1/10 of a whole revolution, which is basically 36 degree. So this is how you can measure the rotational angle. So the minimum revolution you can achieve is 1/2000 times 360, which is 0.18 degree if it is a 2000 pulses per revolution. Now, so this is how you can know what is the rotational angle of your motor. However, you do not know whether it is rotating clockwise or counterclockwise, because clockwise, counterclockwise, you will just receive the same number of pulses. So you don't know whether your motor is rotating clockwise or counterclockwise. To overcome this problem, you add another channel, which is, you can see, physically shifted. As you can see, these two, you can see here, they are shifted physically. So you can see there are some physical shift in the design. So what is the advantage of this thing? The advantage is in the electronic signal, this shift will be corresponding to some delay, lag, and lead. So you can see there is a phase shift of 90 degree. So now your controller can detect whether which channel is leading and which channel is lagging. By monitoring these things, you can understand whether your motor is rotating clockwise or counterclockwise. If leading, channel A, and lagging, channel B, let's say this is clockwise. And if it is counterclockwise, then channel B will be leading, channel A will be lagging. So this smart technique will help you to monitor the uh, rotation, whether clockwise or counterclockwise. But still, there is another problem, which is you are not sure. Let's say you turn off, you rotate the motor and all these things, and then you suddenly turn off the machine. There is no memory attached to this system that will remember where is the location of your motor previously. So hence, you will, for the system, or basically the controller, will forget the previous position of the motor, and it will start from the current position as a zero, and it will start to count the pulses, and it will refer to this current position and get the subsequent positions. So this is a problem. To overcome this problem, so you have another channel. This channel is called index mark. This will have only one window in the one whole revolution. So what we will do initially, before you once you turn off the machine and turn it on again, excuse me, I have to take a call. So please, let's just pause this thing for a while, then we start again. So we are back again. So the thing is, basically you need to have a reference signal that will be detected by the controller only in one whole revolution one time. So what you do is, basically, once you turn off the machine, every time you turn it on again, you have to, in technical term we have to home, H-O-M-E, home the motor, so that until it detects the index signal. Once it detects the index signal, from then onward, we can start counting to channel A and channel B, so that we have a reference, physical reference of the motor location. So that is your 0th location or home location. From there onward, it will start to count the signal. Okay, now let's move forward. So we have understood the three channel A, channel B, and channel C, the index channel. But when you want to use it in electronic signal, what happens is basically sometimes you can get some noise involved. So usually these type of signals are meant to be TTL logic, transistor logic. So which means basically it is 0 to 5 volt. So once you have 0 means it's 0 volt. When you have signal high, number 1, it means 1 volt. Sorry, 5 volt. But sometimes it doesn't really work exactly right, 0 and 5. Usually 3.3 to 5, it will detect as 5 or signal 1, high signal. So what happens if there is a noise in the channel? Let's say you have a nice signal here, as you can see, then there is a certain spike of noise, which is around 3.3 volt. And that noise will cause the controller to detect false signal, false count. So it will count extra pulse as a false count here. To overcome this problem, what we do is basically each channel with a twisted pair cable, so that we make sure that the amount of noise is exactly same on both channel. So we pass this another A channel, channel A, with a NOT gate. So we have a reverse signal. You can see this is off, now A bar is on, and this is on, A bar is off. So it passes through this extra uh, A bar, the NOT gate. Now, once you have this spike of noise, it will be equally, because it is their twisted pair cable, so it will be equally applicable for both A and A bar channel. And once you have these things, when you have something called common mode noise, it can be easily rectified by the amplifier circuit or an op-amp circuit, and you can have a nice flawless signal here, as you can see. Now this is, we can use an subtraction circuit for this purpose, which we will be discussing later part in our course. And this is why, so each channel A, B, C will have its counterpart A bar, B bar, C bar for overcoming the common mode noise. So usually you will have total 6 signal channel for an incremental encoder. This is called incremental encoder. So there are two types of encoder. One is incremental, another one is absolute encoder. So in incremental encoder, you will be having 6 channel. Now let's come to the absolute encoder. In absolute encoder, you do not need to do homing. Rather, you have many disks, not just 2 disks. You have 3, 4, 5 disks. For this one, this example shows 3 disks. So here you have basically these disks are coded as a binary. So you have transparent, transparent, dark window, transparent, transparent, transparent window, all dark window. So let's say if you have 3 LED and 3 light detectors, so for this you will detect all 0, but here you will detect 0, 0, 1. Then you will have 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 1, 1, 1. So this is what you will get. So I repeat, 0, 0, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, and then uh, 0, 0, 0, all 0. So this is how you can identify which segment your motor is, either 0 to 45 degree, 45 degree to 90 degrees, so on and so forth. So this is only 3-bit, but you can have 8-bit, 16-bit, meaning to say you can have 8 disk, 16 disk structure as well, which for high resolution. So now this is we call binary coding, but the binary coding, one problem is that it is simultaneously from one adjacent segment to another adjacent segment. Sometimes you can have 2-digit changing simultaneously. So these two GTs changing simultaneously will cause sometimes hiccups in the machining in the controller. The reason is you cannot maintain exact same times transformation. So one can have a little bit lag and lead, and that will cause a misunderstanding, wrong understanding by the controller, and it will have a jerky motion in the motor control system. To overcome this problem, something called gray coding has been invented. In gray coding, you can see this is binary coding, and this is 3-bit binary, 3-bit gray. Here you do the change for adjacent segment only one digit, one bit. So you don't do any simultaneously multiple bit change for adjacent like 1 to 2 or 2 to 3, 3 to 4 segment. You don't do the change multiple bits, multiple digits. Sorry. So this is that's why you use gray coding. Now, for encoder wiring, you have to understand for 6 signal wire for incremental, and you have a 1 ground wire usually. The most common of encoder used in the industry is incremental encoder. This is because the resolution issue. How? Because in incremental encoder, you can have only 2 disks and you can increase the number of bits in number of windows in the disk. You will have higher resolution. But for absolute encoder, you really have to put multiple disks to increase the number of the higher resolution. Uh, Let me see. Yeah, let's now move on to digital sensors. Other types of digital sensor. You can have inductive digital sensor to detect metallic object. You can have capacitive type digital sensor to detect metallic and non-metallic object. What you can vary is the overlapping area, distance between the two plates. Ultrasonic sensors can be also used for robots and detection for metallic or non-metallic objects. So this is also used. Analog sensors. Now you need to understand what is an analog sensor. Analog sensor is basically sensors that are used for continuous data measurement, continuous variable measurement. So you have to understand the accuracy, precision, sensitivity, and linearity for detecting any analog sensor. So this is a system called thermocouple, where you use two dissimilar metals to detect together, and if there is a temperature difference between the two port, you will have some millivolt range variation, and this is we call Seebeck effect or thermoelectric effect, and this will cause this temperature difference to be detected. You have also RTD, which basically changes the resistance value as the temperature changes. That will, because of the metallic property changes, and higher temperature causes more disturbance in the current flow, so the resistance increases, and you can have this type of sensor calibrated for temperature change. Now you have thermistor also, which is semiconductor-based sensor. Here, when your temperature increases, basically it gives lower resistance. You know, the reason is in semiconductor, the current flow is different than in metallic current flow, metallic conductor current flow. Because in metallic conductor, current flows easily, because in semiconductor you have energy band gap, so you have to apply a heat which will help to overcome this energy band gap, and it can easily allow the electrons to flow from one energy band gap to another energy band gap. But on the other hand, in metallic current flow through metallic wire, you have free electrons. Now you give voltage difference, the electron flows, and it can create the flow of current. But when you give a heat, the electron starts to bombard with each other, and that will cause the net flow to go down. So the current flow goes down, so the resistance basically increases. So, but both property can be manipulated to understand the temperature, to measure the temperature. So here the range has been mentioned for what range to what range. You can use thermocouple, RTD, and thermistor, and accuracy linearity also has been discussed. This is low accuracy, this is high accuracy, high accuracy. This is linearity, high, high, but thermistor linearity is very poor. You have something called strain gauge, which is highly used for stress measurement. As you stretch this gauge, the cross-sectional area changes, and basically that causes the current resistance to change, and hence you can measure the stress and strain. You have something called LVDT, linearly variable transformer, differential transformer. As this core moves up and down, basically the voltage difference between VA and VB changes, and this will help you to measure the distance. Where this is the zero, from the zero you go up and down, and you will have the differences in VA minus VB. This is resolver. Resolver is something like encoder, but what it gives you is basically a continuous analog measurement of the rotation. So this is an analog measurement of the rotation, not like pulse. It will give you continuous sinusoidal wave. Resolver. Other types of sensors include laser sensor, capacitive sensor, inductive sensors, as mentioned here. So in sensor, what are the things you need to consider is the electrical consideration. The output current should be limited. Otherwise, the sensor would fail if you have too much output current. Sensor should be hermetically sealed, horizontal, and so that no dust and other environmental if doesn't affect the sensor performance. Horizontal installation is preferable in this case. Okay, now when you select a sensor, these type of questions I will be asking in your assignment or in your exam. And what is the purpose of the sensor? Whether you should go for analog sensor or digital sensing, what type of material to be used, is it plastic or metal or ferromagnetic? So accordingly, you will detect the sensor, you will choose the sensor for a particular case study. It has to whether space constraint, range, what is the range, sensitivity and linearity you have to consider. So all these things you need to consider for sensor selection. So let's say, for example, ultrasonic sensor can be used for sheet metal thickness measurement in a rolling industry. Optical sensor can be used to measure the proper capping of the container in, let's say, milk bottle industry. Laser sensor can be detected to thin wire, maybe micron range diameter for maybe electronic industry. Small parts of laser sensor. Why small parts? Because laser point diameter of the laser pointer can be as low as 5 micrometer. The inductive sensor is to sense the teeth of a metal gear. For plastic small gear, you can use capacitive sensor or ultrasonic sensor. Capacitive sensor can be used for fluid pressure measurement. So these are some examples. So we can give you similar questions that for so and so case study, what type of sensors you would like to use and give justification. So these are the things that we will be discussing, inshallah, in the next class. Signal conditioning using amplifier. This is very simple inverting amplifier. This is non-inverting amplifier. This is the gain given here, as you can see. We will be discussing this. Difference amplifier. This is the difference between the two voltage input, which can be used. This can be used, if you recall back, for incremental encoder A bar channel to get rid of the common mode noise. This is the adder summing amplifiers to add multiple signal, and this is instrumentational amplifier as well, which can be used detect the V2 minus V1. I think that is all for this lecture. Thank you very much. Assalamu alaikum wa rahmatullahi wa barakatuh. Sorry. Before we move, finish, we have few more things like active filter circuits. So the filter also we'll be discussing in a separate lecture. So you can have the low pass filter, high pass filter. You can have band pass filter as well. You can have band stop filter as well. Later, we will be discussing the signal conversion and generation. So the signal conversion and generation, sometimes you have to have the signal to be converted into current or voltage using voltage divider circuit, Wheatstone bridge circuit, these current voltage converter, all these things we'll be discussing as a separate with mathematical problem. This is first just example. This is a voltage divider circuit. We are not going to discuss this example here, rather in the next class, inshallah. And Western Bridge circuit is something like this. And that is all for today's lecture. Thank you very much. Assalamu alaikum wa rahmatullahi wa barakatuh.